Hello everyone, this is Monica Lupion and today I will cover the lecture 12, Steady State Molecular Diffusion. This is part of the mass transfer concept. As I mentioned in previous classes, mass transfer in general, it's more complex than heat transfer. Especially today, we're gonna study some fundamental concepts and in particular a few very interesting cases where you can apply the different equations of mass transfer. So make sure that you understand everything in this lecture today, and if not, please let me know and I can go with you through the different questions you might have. This is the content of my presentation today. First, the general equation for one dimension. And then we'll see two different cases. Mass transfer without chemical reaction, where I will cover three different cases. One is the unimolecular diffusion, or the diffusion through a stagnant layer. Second is the pseudo steady state diffusion, or when we have a boundary condition that is moving. And third, the Equimolar counter diffusion. Then we'll move to the case of mass transfer with chemical reaction, and we'll see how can we apply the equation in those cases. Then we'll see 2 and 3 dimension systems, and followed by the simultaneous study of the momentum, heat and transfer and mass transfer. Although I'm just going to highlight a few concepts here because we'll cover this study of heat and mass transfer and momentum and mass transfer simultaneously in future lectures. And finally, a summary. If you remember from previous lecture, in general, we can formulate two different equations. This one in green is the general equation of mass transfer. So the gradient of the molar flux plus the variation of the concentration with time minus the reduction of the element A due to the chemical reactions is equal to 0. If we combine this general equation with the Fick rate equation that we covered in lecture number 10, if we combine these two and if we apply the boundary conditions and the initial conditions, we study in lecture 11 that we can formulate a solution of the problem. So for the case of the one dimension, let's see how can we simplify the equation. So the solution of the problems of mass transfer will be much simpler. The conditions that we're going to apply in this lecture today is first, there is a steady state, so there is no dependence with time. So this term here is cancelled. It's one dimension, so we will only consider one dimension, theta. So the gradient here is just converted into a differential with theta. And then we will also see the first of our cases when there is no chemical production, or the same, that the term Ra is equal to 0. If we apply these three conditions to the general equation of mass transfer, this equation here is converted to the d molar flux of A, the theta is equal to 0. As I mentioned, we're going to apply the general equation of mass transfer and also the Fick rate equation. If you remember from previous lectures, this is the equation of the Fick rate when there is a binary system with elements A and B. There are three different cases that I mentioned at the beginning of the presentation. One is unimolecular diffusion, or when we don't have any molar flux of the element B, and I'll tell you more in a minute. the Pseudo steady state diffusion and the Equimolar counter diffusion, which is equivalent to say that the molar flux of A plus the molar flux of B is equal to 0. Again, I will show you more examples of this so you can really understand the different concepts. Okay, so let's begin with the mass transfer without chemical reaction. This is a diagram of the Arnold cell that we used in lecture 10, I believe, to study the Fick rate equation. On the right side is just a diagram of this Arnold cell system. So at the bottom, it's pure liquid of element A. And then here at the top, it's a flow of gas B. And element A will be transferred from the bottom of the cell to the top. Let's apply the two equations that I just mentioned. First, the general equation, and second, the Fick rate equation. If you remember from a few minutes ago, I mentioned that if there is no chemical reaction, if it's a steady state, and if it's only one dimension, then d of the molar flux, the zeta, is equal to 0. That means that the molar flux of A is constant. The same will apply for the element B, because we can apply the same equations but considering B instead of A. So because of the one dimension steady state conditions and the that there is no chemical production, we can we know that the molar flux of A and B are constant. If we pay attention to this line here with zeta is equal to zeta 1, we know that there is no transfer of the element B. Only element A goes from the bottom to the top. So here in this line, there is 0 moles of the element B. Therefore, since the molar flux of B is constant, and if in this particular point is 0, it has to be 0 all along zeta. So this is the condition for the unimolecular diffusion, that the molar flux of V is equal to 0. We can also, sometimes we call this system or this element B as stagnant gas. If we apply this solution that we just found out to the Fick rate equation here, we can cancel this term, and therefore the molar flux of the element A will be equal to the minus concentration, the molecular diffusion coefficient, over the 1 minus the molar fraction, dy d zeta. We can solve the problem just by applying the boundary conditions. In this case, when zeta is equal to zeta 1, the molar fraction is equal to the molar fraction 1, and when zeta is equal to zeta 2, the molar fraction is equal to a different value. If we directly integrate the previous equation and apply these two boundary conditions, the solution is indicated here. So the molar flux depends on the concentration, on the diffusivity or molecular diffusion coefficient, the length of this probe here, and the variation of the molar fractions. If we define the log mean concentration here and play around with this equation here, we can get to this equation box in blue, which is the general equation for unimolecular diffusion. There are many examples in industry that we can consider its unimolecular diffusion. For instance, absorption, humidification, and there are others. Second situation is when one of the boundaries moves with time, and we call that pseudo steady state diffusion. We can apply the very same equation that we just defined for the case of the unimolecular diffusion. So this is the equation that we're going to use, but in this case, the length of the proof will be a parameter because that will change with time. We define that at theta, where theta is the difference between the length at the top minus theta, which can be changed with time. So theta is a function of time. That's the main difference between this case here and the case of the unimolecular diffusion that we just covered. In order to be able to solve these equations, because one of the boundary conditions moves with time, what we're going to do is to apply the equation of mass balance of the element A, and that equation will apply to any situation that you might have. And it's always the same. Whatever comes in a control volume minus what it comes out plus whatever is being produced within this control volume has to be the same or equal to the accumulation. We in the control volume, in our control volume, there is nothing getting in. It's just a source, so there is nothing going in. But there is a molar flux of A getting out. We're not producing anything new. So the molar flux of A that is getting out times the surface has to be equal to the molar of A that is being accumulated. And this is defined as the density times the surface over the molecular weight and the variation of theta over time. If we play around with this equation here, we can define this equation box in blue. That is the general equation of the pseudo steady state diffusion. If we solve this equation here, there is a relationship between the time and the position of this boundary condition changing with time. Third case, Equimolar counterdiffusion. I would say that amongst those three cases, the unimolecular diffusion and this Equimolar counterdiffusion are the most important ones. We'll see some cases when we apply the pseudo steady state diffusion, but most of the time, if you really understand the unimolecular diffusion and the equimolecular counterdiffusion, it should be okay. For the equimolar counterdiffusion, we're going to follow the same procedure, the same methodology. So we apply first the general equation of mass transfer, which in the case of having steady state conditions and no chemical production and only one dimension, it is simplified to the variation of the molar flux with theta over the variation of theta equal to 0. For the Fick rate equation, now because it's counterdiffusion and it's equimolar counterdiffusion, that means that if there is a variation of the molar A, it will be the same variation in the molar B. And this is just an example when we can apply the concept of equimolar counterdiffusion. So if there is a tank of ammonia and a tank of nitrogen, and there is a mass transfer between the tanks, the transfer will be 1 molar of A per 1 molar of B. If you apply this concept of equimolar counter-diffusion to the Fick rate equation, this term here will be equal to 0. So we can just simplify the Fick equation. We will only consider the equation when there is mass transfer due to the diffusivity, to the gradient of concentration, and not due to the bulk motion. If we integrate, combine these two equations and integrate, considering the two boundary conditions indicated here, this is the general equation boxed in blue of the equimolar counter-diffusion mass transfer. What happens if we play around and we apply this boundary condition and we solve the equation? Well, then this is a requirement that all the systems having equimolar counter-diffusion must comply. So the difference on the concentrations has to be the same as the difference amongst the position zeta. And in general, we say that if there is any process where the bulk contribution is very small, for instance, when we consider dilute systems, we can directly cancel this term here in the Fick rate equation. So this case is very important because it doesn't only apply to equimolar counter-diffusion when we have that 1 molar of A per 1 molar of B. But in general, if there is a process, for instance, dilute systems, where the bulk contribution is very small compared to the diffusivity, then we can always apply this general equation for equimolar counter-diffusion. Okay, this is a simple example that I would like you to try, and of course I will be also post on UBLearns the solution of this example. Okay, those were the cases when we didn't have any chemical reaction involved. What happens if there is a mass transfer with chemical reaction?